So first of all, thank you for the interview. Let's start from this book. While I researching the history of China AI, I found that social scientists and philosophers play a significant and positive role in the early stage of AI development. Yes, this made me curious about the European experience. So, from your perspective, as the president of European Academy of Science and Arts, so what has been the role of humanity and social science in the history of AI development in the Europe?
Yeah.
Yeah. So, how do you perspective the historical relationship between these two cultures? That is, the science and the humanities within the Europe's AI development.
Yeah.
Yeah.
Okay, that is a nice question because the connection between China and Europe dates back at least to the late 17th century.
Yes.
Because my favorite scholar in Germany is Leibniz. And Leibniz, you know him,
Yes.
famous mathematician and philosopher. He, in the end of the 17th century, has first ideas inspired by China. That was the I Ching. That was the I Ching. Because they had the idea of binary symbols. You know that.
Yes.
With the broken line and the straight line, these symbols, which
I see.
a kind of code of the natural forces. That was the idea. And he was inspired by that because in the end of the 17th century, there was a close connection between the French Jesuits, that was a religious group, you know, to China, to the empire. And then actually Leibniz was a diplomat at the French court. And so he had this kind of connection. He was inspired by this binary system, and then he invented an arithmetic of binary system. And
I know this story.
Yeah.
Yeah.
And Leibniz was a mathematician. He had not an idea of electronic advantage. That means that the switch off and switch on is symbolized by these two binary states.
Yeah.
He was only inspired by the idea of mathematics. He thought that is the simple representation of numbers, not the decimal numbers, such as in Europe, but only with two symbols, 0 and 1. That was his motivation. It was more or less forgotten, but then in the 20th century, people like Turing came up with the idea of the digital computer. And now the next highlight connection that was in Europe, Alan Turing with the concept of a digital computer. That was a Turing machine.
Yeah.
And all ideas of modern digital computing were just in this famous paper of 637 in the Royal Society Annals. And what I mentioned in my talk, namely, this undecidability problem, that was the starting point for Turing, that there are, in principle, from a logical perspective, there are problems which cannot, in principle, solved by a digital computer. And that was his famous vaulting problem. The question, is there, in general, an algorithm which can predict for any input that a Turing machine will stop after finite steps or not? That is, in principle, not decidable, because if you define an, in principle, undecidable, non-computable real number, then the assumption that there is such an algorithms which can do that would contradict to this definition of the non-computable real number. So it is very simple. The diagonal argument, I will not go into the details. Actually, it is a logical problem. That means that cannot be overcome by acceleration of digital. That is a restriction. Now, people at first thought, oh, that's interesting for philosophers. And then Gödel, you know,
yes.
Goethe's incompleteness theorem of formalism of a certain degree of complexity. That is, by the way, only a consequence of the undecidability of the halting problem of Turing. Anyway, there's the basics, digital computing. And that means all our computers now have a restriction. There are in principle problems which cannot be solved by that. Now, at first, the people thought, oh, that is only interesting for logicians and philosophers. But then that was in the time when I was studying mathematics and logic. That was in the early 70s. And I remember that in 1970, a Russian mathematician from Leningrad, that was St. Petersburg nowadays, that was Matyashevich. He came up with an amazing result. Namely, he proved that one of these famous problems of Hilbert's list of, at that time, not solved problems. That means they are not in principle unsolvable, but it was not known. Are they solvable or not? And he had more than 20 problems of that kind in a list. And one of these problems was the 10th problem.
Yes, you have mentioned in the...
You remember that? And that was the diophantic equations. And then Matyashevich proved, the rigorous mathematical proof, that the diophantic problem is mathematically equivalent to the halting problem. And that means you have a mathematical problem which is in principle with a digital computer not decided. And what I highlighted here in my talk,
yes,
that has consequences for modern computing, because 20 years after these results of Gödel, Turing, and so on, it was proved that if you consider not digital numbers, but real numbers, then it is solvable. That was Tarski. And that was also theoretical results, because actually we do not have an analog. But now with these new ideas, which I presented here on neuromorphic computing, there is a chance to have a new kind of computers which are brain-oriented.
Yes.
And that will follow this line and solve these problems. That means the in principle digits of the in principle restrictions, digital computing can be overcome by this kind of real computing. Real computing means computing with real numbers. And technically, the realization would be analog computer in the sense of neuromorphic. That is the line from the beginning, from Leibniz up to.
Very interesting. Yeah. And let's come up to the book series of the Advance in Complex Systems, Artificial Intelligence, and in emerging technologies. What was the inspiration behind this book series?
Actually, my work started with two routes. One I explained before, that is from Turing, the digital computing, up to the modern explication. And the other one, I studied mathematics, physics, and philosophy, logic. And that was inspired by physics. And in physics, you have these nice applications of statistical mechanics for complex systems. Complex systems only means a system with many elements. And people are sometimes afraid because they thought, oh, these complex systems are not computable. And you know from physics, Laplace believed in the beginning that the universe can considered as a closed system which can be described by mathematical differential equation, which all are computable. That was the belief of
Yes.
Laplace, great French mathematician in the beginning of the 19th century, and in the end of the 19th century, also a great French mathematician, namely Poincaré. He came up and he proved that even in the case of a closed system, complex closed system, there may be these interactions of more than two elements, the many bodies problem, and then he rigorously proved that with the standard mathematical solution methods, it is not possible to solve these many body problems of interaction. That means in practice, for our astronomers, you only have approximation numerical solution, not a rigorous exact solution or a closed system. And then what I highlighted also in my talk, and what was crucial for my work on this topic, was to consider open systems.
Open system.
Because open systems are, closed systems are more or less a mathematical abstraction. Open systems you have in biology, you have in economy, everywhere. That means the system is in interaction with its environment. And then the basic idea here is that at critical values, the system has two options. On the one side, two structures emerge. It's a phase transition of second order, contrary to one order, that was the closed system. And then that was a result in the 80s, 70s, 80s of the last century, that people for the first time find approximation methods to explain the second order phase transitions in open systems. And that was a possibility to describe in a mathematical rigorous way the emergence of new structures in open systems, not only in, so to say, dead systems like a chemical, the emergence of structures, but also in the life science. We have a mathematical model now to explain that. I showed these nice example of these patterns on the wings of a butterfly, very picturesque. And how is it possible that this kind of order can emerge? That can be described mathematically by the second order phase transition.
All right. So what primary goals you hope to achieve with this book series?
You mean complex systems, artificial intelligence in World Scientific Singapore? Yeah. Now, I was so in the theoretical explanations. You're coming back to that, very practical. Yeah, my idea is a complex systems approach is a very basic level of mathematical explanation of complex systems everywhere. It is not only in physics. We until now, we're only discussing about the applications in the natural sciences. And that is a lot, because it does not only mean physics and chemistry, it only also means the life. So my idea is, and my book, my first book, on thinking in complexity, that was already, and that was a success of this book, because I did not only consider applications in the natural sciences, but also in economics and in the social. That means that an economic system is also an open system, the market, the stock market. And I did a lot of work, even special monographies on the explanation of the, for example, turbulence in markets. How can it be mathematically described? And it is done by mathematical physics. Mathematical physics means not theoretical physics. It means a method of mathematical methods of physics, but now applied, for example, in economy. And so that is sometimes called econometrics or something like that. And it's amazing to model these highly complex markets. But the disadvantage is it is not in the Laplacian sense. You cannot predict, like in Laplace system, a prediction for the constellation of certain planets exactly in a rigorous way. But anyway, you can model the sensibility of phase transitions. And so at least you can get, even in economics, I think, an early warning system for the critical values. Then you can, or in the climate model, same. You can say, oh, we are now running into a situation, if we surpass these threshold values, then the whole system becomes uncontrollable. That is a great advantage of this kind of modeling. Now, all that was considered in that book. And what I thought already in the early 90s was modeling here the differential equations. That is nice mathematically. You have these standard models, but if you want to do that practically, for example, application to the Chinese market or to the European market, then you have to handle a lot of data. You know, in principle, the algorithms and mathematics, but we know now from machine learning, it depends massive data. Large language models, large, and so on.
Yes.
Yeah. And now AI came in. That is the background of this explanation. We have this nice approach of complex systems, and now artificial intelligence. And when I came up with this idea, some of my famous elder colleagues, they wrote me, wonderful idea, the connection of complex system science with AI.
Yeah.
Because AI opens the possibility to do that.
Yeah.
Because we have now the powerful machines to handle these complex data. Now, to make a long story short, that is the main motivation. And then the third term is emerging technologies, the idea that in the combination of both approaches, the new breakthroughs become.
Yes. Yeah. So in your view, what is the most significant gap between the complex theory and the applications in the AI? So how can this book series can help to bridge it?
Yeah, modern AI is different to the historical origin, which we discussed before. Because the historical origin was very logically orientated. That was my beginning. My PhD was exactly on the line of Turing. And that was nice. And by the way, that's sometimes forgotten today. But
no, it's neural network.
This line is still a topic in science nowadays. Because what I'm also engaged in is what is nowadays called proof assistance. That means that you have systems, logical systems, which are able, on the basis of automated proofing. That was an idea which came up with the symbolic AI in the Turing tradition, that you can automatize the proving in mathematics. Yeah, it can be done in some sense by special programs. And for example, it's an old idea in logic. If you have logical formalism, then you may be interested, is the formalism correct? That means all formal derivations in these systems. Does it represent a true proposition in the theory? Yeah, it's the idea of logic, formalizing by formal propositions, and then formally by a machine deriving these conclusions. And then the question, is the machine in the end formally proving truth in the theory? That is correctness. That means that we call that satisfiability, that the formalism can be satisfied by a true model. That was a logical idea, well known since the days of Gödel and so on. Now the application in computer science was, instead of a model, we consider a specification. If you have formalism to describe the production line in a car industry, then is your formalism correct in the sense that the steps which are formally derived describe exactly what is going on in the physical production in the car industry. That is correctness here.
Yeah.
Now, that is the satisfiability result, and in logic, a lot of methods were developed, the so-called resolution method, which is still in use today. That means people are studying in Germany, in Stuttgart, there is Daimler-Benz. And I know that for the logistics in Daimler-Benz, for selling cars, every customer had different interests. Someone wanted a car with this equipment. And so on. This organization of all these requests of the clients is formalized and is done exactly on these ideas. Now, concerning mathematics, we can go a step further. Namely, in the end, the idea is that in software engineering, in the programs, we must have a control mechanism that your software program is exact and you can rely on it. And in the sense, in the way I described it before, with the correctness proofs in logic, that is done nowadays with so-called proof assistance. That means you have a rigorous logical formalism, which is testing that your software is doing what you want that it should do in the sense of correct. These are the proofs. So what I want to highlight here, an old idea of mathematical logic is still nowadays applied as proof assistance. These are the famous, and I highlight that because every year since 2016, we have in Munich a so-called International Autumn School, which is dedicated to these proof assistants. There are logicians, mathematicians, computer scientists. We are doing that because nowadays we want to apply it to these very, very complex programs in modern machine learning. Because nowadays the software is no longer these software programs in the past, in the tradition of these traditional AI. But nowadays we have machine learning. And in machine learning, we have the neural networks and we have a statistic. So the question is, how can you find proof assistance to control these complex statistical approaches? Yeah? In the classical approach of AI, you have logical systems.
Yes.
That means in the center are logical deduction. That is the idea. But in the center of modern machine learning is statistics. So from a methodological point of view, in the center is induction. You start with a sample because you are learning from finite samples, like in your practical experience. And then by expectation, by calculating of statistical expectation values, you try to generalize it.
Yeah.
And that is the approach actually everywhere in the empirical sciences. Logical deduction is only in logic and mathematics.
Yeah.
But in economics and in natural sciences, you start with your laboratory, your results in the lab, finite measurements and samples, and then you try to generalize and to find some correlations, statistical correlation, and to generalize it.
Yeah.
That is statistical induction. And that is the challenge of modern machine learning. And our idea is, how can we control? Because nowadays, the machine learning, the people are totally crazy with their possibilities of machine learning and profit-oriented. And but what we are in danger to lose is in the ANSI control. What is going on with our statistical machines? What are they doing because of this immense mass of data? Nobody knows in the mass of data which failures are hidden there and things like that. And therefore, this old idea of proof assistance is very crucial. And I'm working on that. So in the end, my message is bring together the, in quotation mark, old rigorous tradition of logic and AI together with the modern machine learning, the statistical.
Yes.
Sure.
Yes, that's true. The mathematics is the fundamental of the modern AI,
Yeah.
and people, as you have mentioned, people may get crazy, but for the AI, we can use mathematics to prevent AI getting crazy.
Yeah.
Yeah. So then I have some question about the philosophy on the AI and complexity. Your book series also focus on the philosophy of science and technology.
Yeah.
And now we can see a lot of generative AI. So to what extent do you believe this generative AI is challenging our traditional philosophical concepts of knowledge, creativity, and even reality?
Yes, that is, of course, a very crucial question. To my experience, we are now in a period of amazing success of machine learning. It means the statistical machine learning. But the question is, although statistical learning is so successful, is it exactly on the line of human thinking? And I think it is not the case. The reason is, you know, in engineering sciences, the engineers were successful not by exactly simulating nature. Consider the flying bird. Yeah. In the beginning, the engineers thought, oh, we must simulate the bird, and but they were not successful. They had the idea we have to consider the foundations of aerodynamics.
Yes.
The mathematical equations, and then we can use it to find quite different approaches. Nowadays, our aircraft, tons of weights can be brought to the sky and so on. That was not possible in nature. So it was a new idea. My point is here that the breakthroughs in engineering, that's also true for cars and things like that. In the beginning, there were the horses. They tried to simulate the horse as a power engine, but or the humans. But then they found electrical motors and other motors quite different. So that's my point here. In modern machine learning, we find it is only inspired by the neural brain. But the engineers are not interested to explain the human brain. The neural networks nowadays, there are a lot of rules to explain in the technical neural networks the algorithms, not only by these linear rule, Hodgkin and Huxley, I mentioned it in my talk, summing up the neighbored inputs of the neuron, that was measured there, that is confirmed in the brain, but there are a lot of other rules nowadays invented by the engineers by reasons of increasing efficiency, which were never discovered in the brain. If you have a successful neural network in technology nowadays, there are architecture which are completely different to the human brain as far as we know. For example, convolutional networks. That is a technical invention. It's mainly used nowadays in technical application, but that is never found now in human or animal brain. It is a technical invention, but very successful. Now, that is my point concerning also in general the statistical machine learning nowadays. Statistical machine learning is very successful, but it works by using big data, a mass of data. You need a mass of data. And now consider the history of science. In the history of science, Newton, very poor data. It is not true what Voltaire said. Voltaire did the propagation of empirism. That means the people had the idea, oh, the natural scientists are looking to nature and they are collecting data and measurement and measurement and measurement. And then they had the genius idea. The gravitational law was not found by looking to falling apples. You know, Newton was the son of a farmer, and he had the idea to combine Kepler's law with his famous second law of mechanics. That was an axiom, a theoretical axiom, that every effect in nature is caused by a force. Force in the sense of Newton, famous second law of mechanics. And that was combined. Then he finds this theoretical model, and then unbelievable. Everything could be explained. The same is true for Einstein with his famous equation. Einstein had very poor data. And the people were shocked and amused by his predictions. Totally crazy in that time. But nowadays, it's a law which is confirmed. And you understand my argument. This statistical approach is mass of data with algorithms. And that is not human creativity. It is, in some sense, some parts of human intelligence is working by learning from data. That is true. But the success nowadays with this amazing mass of data, our brain is not able to do that. For example, very practical example, I considered that, let us imagine the time of Newton again. And then Newton has ChatGPT or DeepSeek. And what is the strategy here? To have all information in the world about these kind of effects. And then it is seeking for a formula on that. And then it comes up with people are shocked and cannot explain that by statistical meaning it is possible to solve very ambitious mathematical problems nowadays with ChatGPT. But it is possible because all kind of books and documents in this mathematical field is fed to the machinery. But ask a pupil, a girl or a boy at the school to solve a certain problem. And sometimes intelligent young people came up with a solution, and the teacher is shocked. And he said, oh, that I never had this idea. Yes, they are right. that is human creativity. And it is not completely explained by statistical learning. For example, causal thinking, and that is a point I'm also interested in. Causal thinking, that is on the line what I explained with Newton and Einstein. That means this idea that the new laws in nature or society are not only found by summing up data and learning by these learning algorithms, but by causal, what I call causal thinking. And how is it possible? You know, in medicine, it is not so interesting to find statistical correlations between a certain chemical substance in correlation with, for example, the emergence or growth of a tumor in cancer. Yeah? You found, okay, there's statistical confirmation, and now let us produce this kind of medicament with this kind of correlation. The much more interesting question is, what is the cause of the growth of a tumor of cancer? What is the causal model, the origin, in order to find a successful treatment? Yeah, and that is not at the first glance, not the approach of modern machine learning. Machine learning means summing up data. Causal learning is something different. There are approaches, perhaps that's too much to go into details now. We are considering that, for example, there's a Max Planck Institute in Germany, in Tübingen, which is engaged in this causal learning approach. And it is possible to some degree to have a kind of pattern recognition in data for causal relations. And I will not go here in the details, but to some degree it is possible. So my idea is that in the future, we have some programs which, at least for restricted domains with certain features and characterization, for example, specialized fields in medicine, you have data mass with this fulfilling this features, and then you have a tool which can recognize the causal interaction, the causal relations of these interaction features. So it is not, of course, these great applications of Newton and Einstein, but at least in the future for these restricted domains to have even causal thinking. But that is a new direction in the development of machine learning. It is not the classical machine learning. Now my point is statistical machine learning is not the last word. It is very successful nowadays, but in the future we will have and we will need new breakthroughs to go on in this unbelievable potentiality of human creativity.
Yeah, that's true. Human can get knowledge with the few data, but AI cannot.
Yeah. Until now. That was also a point in my last slide. They would never say never.
Yeah, never say never.
In the past, we said, wow, that is the restriction of formal thinking. I remember when I was studying student and I came into philosophy, then I know, oh, this guy is coming from the mathematics and logic. At first, we will say him, oh, since Gödel, formalization is restricted. Nonsense. My PhD was on these ingenious early ideas of Turing that is not so well known. The Turing dissertation was not this famous undecidability problem, this famous paper, but he was doing proof theory and the first steps of modern proof theory in mathematics. And then Turing has the first ideas, very similar to Gödel, to extend the classical proving systems by more complexity degrees, in the sense what is beyond the undecidability problems. And so I said, no, perhaps you know there's a famous German logician who died relative early. His name is Gerhard Gentzen. And Gentzen had the idea, Gödel proved that the consistency of formal arithmetics is not decidable by methods of the theory itself. That means by mathematical induction on the natural numbers. But then Gentzen came up with the idea, if we extend mathematical induction not only to the digital numbers, but to the so-called ordinal numbers, that means transfinite number, then you can prove the consistency. That was the first hint that there is a world beyond, and you can go on and you can overcome the limit. I remember my colleagues, I was a student at that time, they were not very amused by this news, because they were happy as philosophers. Oh, we have no restriction.
Yeah,
now, the method is, and that is also true for machine learning. Machine learning, I have these discussions with my colleagues in philosophy. They came up and explained me, machine learning statistics cannot explain human creativity. That's right, only to some degree, but it can be overcome.
Yeah.
Yeah.
Well, we can see the massive investment from big companies such as OpenAI, Google, in artificial general intelligence.
Yeah.
Yeah. So how do you view this race of AGI? So, in your opinion, is the greatest barrier to achieving AGI a technical challenge or a fundamental philosophical problem?
Yeah, of course, that is exactly on the line which I explained before. So in general, say never, never.
Yeah.
It may be possible. Nobody knows exactly. But what we can do, and that is also, feel that is my task, that I very rigorously analyze the limits of a certain tool. All our algorithms are tools, even our AI algorithms in machine learning. And I'm always interested at first to determine in a rigorous way the restriction of the tool. That is the task of an engineer. You have a nice instrument since antiquity, but a hammer cannot be used to solve every kind of problem. And that is true also for these modern, highly tricky algorithms. But it's then, if you have the limits, you can ask for the extension of new. Now, coming back to general artificial general intelligence. If the artificial general intelligence means the human abilities, then we have to consider one crucial point. All our methods, mathematical methods, are simulations. That means even if you, in a modern robot, we can simulate not only the speaking by the chatbot, but also moving and things like that. You can train a robot. Recently, I saw a dancer and an artist. And then he was equipped, or she was equipped with sensors, and by that they got a lot of data, a data model, and that could be simulated by the computer. And the robot, if you have the technical equipment, is advancing more and more in an elegant way nowadays. That is possible. But now coming to the question of the philosophical question of artificial general intelligence. The dancer, that is not only the stimulation, it is an expression. That means the dancer, now the crucial point, is feelings.
Yeah.
That is not only simulation. It is an emotion. You can, with machine learning, simulate all kinds of emotional expression. I have no doubt that that is possible. But the difference is for the creativity. For example, a composer also to have a certain feeling. For example, Beethoven, the famous composer. It is known that he was walking in the Wienerwald, the forest of Vienna, round about Vienna. And then he was inspired by the atmosphere and the pastorale, his famous symphony. That was an inspiration which he has. Of course, as a technical trained composer, he was trained to write down the sequence of tones in a rigorous way, like a mathematician. The famous mathematician must not only be able to write down correct formulas. To become a Beethoven or to become a Gauss, famous mathematician, or an Einstein, or whatsoever, you must have ideas.
Yes.
And this kind of innovation is something very different. If modern machine learning is able to compose, then it is in the end always a simulation. Modern chatbots can be produce melodies, for example, at certain degrees of difficulty. You can say, oh, I want to have for a pupil of the middle level of education, something like a melody. Or I want to have a very ambitious new creation in the sense of Beethoven, for example. Then the machine is doing that, but it is not Beethoven.
Machine has no emotions.
Yeah, and so what we call in philosophy, in phenomenology, in the philosophy, that was in Germany, Husserl, and in the 20th century, and he inspired the French philosophers such as Merleau-Ponty. And in the contemporary discussions, that was Dreyfus, they underlined what is called embodiment. That means that people are also have a certain feeling of that. Now, the crucial question is that an absolute limit for this artificial general intelligence? Maybe that in the future, we are able to create something like living tissues, to create something like that is biology. Neurobiology is also developed, not only computers, neurobiology. And we are more and more in the possibility to create artificial cells, living cells. And it's amazing. And so in the future, maybe, we don't know, but actually I have no doubts that that will be the future, that we can create organisms which by new chemical abilities can also have these feelings. That means kind of experiences. And then it could be possible to have in the end even these embodied entities which are able to be creative. Until now, it sounds like science fiction. But actually, it is on the line of potentiality. For me, also as a philosopher, the question is, should we do that? Should we do that to have organisms which are created by us with a kind of own evolution, with a kind of own embodiment, with a kind of own feelings? You know these scenarios which are, there was in the past a very interesting science fiction movie. It is called Ex Machina. Perhaps you know that. And that is exactly the situation. That in a closed house, the ingenious computer scientist and engineer is living together with his creatures. These are very smart humans which he created, who, one must say, who have their own feelings. And then they have their own will. And then, of course, science fiction, there was a conflict between the creator. It's like in the Bible, by the way, with God and his creatures and all these things. But I think that will not be excluded in the future. But it will be a challenge for us from an ethical and from a legal point. Engineering is not all. How far should we allow this kind of innovation in the future? And that will be a great discussion in the future. But from a technical point of view, it is not exclusive from my point of view. And I do not see any, in principle, limit for these kinds of development.
Yes, embodied AI is hot nowadays, and maybe the machine can express the emotions in the future. As you say, never say never. We are go beyond the Moore's law. We are breaking the von Neumann's architecture. Mm-hmm. So maybe it could be. It could be done in the future.
Yeah.
But as AI becomes more sophisticated, how should we redefine the intelligence itself? And is Turing test still a benchmark?
Uh-huh.
Or we need a few new frameworks to understand the non-human intelligence we are creating?
From a mathematical point of view,
yeah,
even modern AI, machine learning, is actually based on the Turing style.
Yeah,
that was my point here. Because if you consider even a modern supercomputer rigorously, then you have the hardware, and that can a little bit differ. You have now the GP, CPU, the GPU with the graphic. That is the OpenAI is doing that. It's more accelerated, but in principle, it is the old architecture. And that is in the Turing style, because in the Turing machine, you have already the separation of the processor and the memory and things like that. And these are the logical principles. And then you have the hardware, which can nowadays realize in a different way, such as in the beginning with the electronic machinery of John von Neumann and so on. But the architecture is more or less the same. And you have the hardware. And on the next level of the hardware, you have the operator system. German, we say Betriebssystem. And then there are the different layers of languages up to the programming language, which is closer and closer to the human user. That even people who have no ideas of what is going on in these complicated machinery, they can use here the computer on the user level. So on the basic here of the hardware, the first level, that is still computable function. That is a theory of recursive functions, such as in the time of Turing, Kleene, and all these people in the 40s and the beginning of the 50s. And therefore, still in education, in theoretical computer science, the students until today, they learn the theory of computable functions and things like that, because that is a mathematical basics, and that is based on Turing. Yeah, that is my idea. It is forgotten because nowadays we have all these amazing applications of computer science. Nobody is aware, mainly people who hate mathematics. They are using
I hate mathematics.
They have no idea that on the basic there is mathematics. This theory of computable functions.
Yes.
Nothing else. Has nothing changed. Yeah. But these, so we are still on the Turing style. It would perhaps change if we came up with these embodiments. But now I like Turing. I admire him.
Yes, me too.
Because Turing was absolutely ingenious.
Yeah.
Turing, in the last years, you know, he had a terrible fate, and he died very early.
Yeah.
And 2 years before his tragic death, he published 2 papers which are completely different to this, and that is complex systems.
Yeah.
The title was Morphogenesis in Chemical Reactions, something like that. A completely unspectacular title. But what he did was topic which I started with. That was also Turing. Nobody, I think, in the audience was aware of that. Complex systems. Because Turing had the idea to consider a very simple system of chemical reaction. And in this chemical reaction, he considered dissipative interaction. And his idea was it's a very simple system with only 2 units which are interacting. And then it is described, in his case, by linear equation, the state transitions. And then he showed if these 2 units are coupled in the sense of a dissipative interaction, then the system is destabilized. And this was the starting point. It's absolutely unspectacular. But in the next step, a famous American mathematician, his name is Steve Smale, came up some years later, a paper which was published by the American Society of Mathematics. He came up with the idea, let us generalize this Turing system with linear equation, because linearity can only demonstrate destabilization. Let us consider it a little bit more complex, namely nonlinear. And in this case, mathematically, very theoretically, he could prove that there is a chaotic solution. That means a complex structure is emerging. And that is the breakthrough, what we did, and I published about that, to do that not only for the specialized application of Smale with a special nonlinear equation, but to consider that in general for all kinds of reaction diffusion equations. And then we could say for this class, differential equations, at least we can explain and compute all kinds of emergence of complex structure. So my point here was, because you asked for the Turing line, that even the other approach of the book series, namely complex systems, not only artificial intelligence, is actually rooted in the idea of Turing.
Yeah.
He was in the beginning the godfather of both.
Yeah, you like Turing so
That's
much.
amazing. It's not aware by the computer scientists because they, in general, are not aware of these last papers of.
You have emphasized the quantum computing in your talk. Do you foresee quantum computing the most profound cooperative effect on the AI on the next decade?
Or you mean neuromorphic computing? Yeah.
Yeah. Or do you think there are other technologies and AI have a similar cooperative effect?
Yeah. That was my point, and I was asked of that after my talk in the discussion, namely the relation of neuromorphic computing with the other a great perspective nowadays, which is very hot and discussed, namely quantum computing.
Yeah.
And quantum computing connects the machine learning with, I think, in the 20th century, in the natural sciences, there were, besides these beginning of computing with Turing and others, the other great breakthrough in physics was quantum. And quantum physics is because it describes these actually, as far as we know, the basic laws of our universe. That was the idea of Feynman. Feynman, this great physicist, who said, "Oh, it was relatively late. It was in the 60s, I think." And then he said, the classical computer is only simulating the classical world. Let us do that for the quantum world, because the real world, as far as we know, physical world, is quantum. And so let's start here with the quantum. That was a basic idea of quantum computing nowadays. And nowadays we are in a phase of development that these basic ideas of the 20th century are applied in quantum computing. Coming back to the title of my book series, Emerging Technology. 20th century is an amazing century concerning all the basic ideas of modern science. That was relativity theory, quantum physics, mainly by theoretical people with less data again, and Turing with computing. But nowadays, I think the 21st century is mainly dominated by engineering. That means it is a basing, therefore, the third part in my title, for emerging technologies. Breakthroughs here, that is quantum computing. Quantum computing nowadays is in a stage, we have already the mathematics, namely from the 20th century, more or less. But it is very tricky now to build a quantum computer. But it is done more and more, and the quantum computer is still realized. Not the technical quantum computer, but we are now in a state, and I'm engaged in Munich in this research group, that the quantum formalism is already used to simulate quantum computation on classical computers, namely on supercomputers. The classical supercomputers, which is still a Turing machine, is very powerful, not as powerful as a quantum computer, but to some degrees, you can simulate quantum computing. It needs, of course, the classical computing, a lot of energy and data. You need these powerful supercomputers. But to some degrees, you can already solve these optimization problems, which I mentioned this morning. That means you use the quantum formalism but it is simulated on a classical computer. So to some degree, we have already these applications. And quantum computing is, the quantum mechanics is amazing. You all know that the new aspects which extend the classical physics far beyond on its possibility, very new principles which were not known in classical physics, the superposition principle. And if you consider the Nobel Prizes in the last years, in the last year and in this year, they also are related to these breakthroughs.
Yes.
Quantum tunneling was well known since the last century as a possibility in quantum in quantum mechanics, and also these points which I mentioned before, the superposition principle and things like that. But nowadays we find the technical application. For example, here in China, that's concerning innovation. In my old continent, Europe, the people had a lot of nice ideas. All that was more or less found in Europe. The breakthroughs, technology, they are mainly not in Europe. They are in the US or here in China. For example, the quantum communication. The idea goes back to Europe. That means to Niels Bohr, to Einstein, still in Europe in that time, in 1935.
Yes.
They had the idea of the Einstein-Podolsky-Rosen relation. And then it was confirmed also in Europe, in Paris, in the beginning of the 1980s by Aspect. And that was the confirmation of entanglement. But now the idea came up, that was also still in Europe. That was also Nobel Prize winner, Anton Zeilinger from Vienna. And these people had the idea to do that. He was a physicist, actually, to do that for quantum communication, the entanglement of sender and receiver. And they did first steps in Europe, but in the end, China did it because he had co-workers from China. And these people are now in the head of great research projects here in China for the quantum internet with satellite technology. My last slide. And
Hanjian will also study in the Europe.
Yeah.
Yeah.
And that is a little bit a pity, a problem, which we have to discuss in Europe, what we call in economy innovation. Innovation is not only invention. Yeah. Tesla, for example, this ingenious engineer, you know, he was a Croatian. But then to become such a successful engineer, he went to the US, and then he could realize it also on the market.
Yeah.
Or another example is the rocket. The rocket was found in Germany. That was Werner von Braun in a very dark period of our history. But after the Lost War, he went to the US, and together with John F. Kennedy, they built the rocket to the moon. That is innovation. And the same is true nowadays for China. Yeah.
Thanks for
I have no explanation. But what is necessary, and that is typical for the 21st century, I think the breakthroughs, and therefore in my book series, not only complex systems and artificial intelligence, but complex systems, artificial intelligence, and emerging technology. That is the vision of our century.
Yes. Yeah. I have a question about the AI social impact. Expandable AI is a key point, but in the practice, we are often face a trade-off between the model's performance and its expandability. So, how should we solve this problem, especially in some high-stake domains, such as the medicine or justice?
Yeah, medicine, to come back to my talk, you remember that I mentioned an application of these theoretical problems concerning the undecidability and so on, which can be overcome by neuromorphic computing. And that, if I tell that to people from the engineering side or from the more applied side in technology in the companies, they said, oh, that's very interesting, but it doesn't matter. It is nice for the mathematicians to know that there are problems which can be solved by these new kinds of, now, whatsoever. What should that? Now, recently, I think it is 1 or 2 years ago, in the Munich research group, we found it was especially done together. I was a little bit involved in that. That these undecidability problems have consequences, for example, for medicine. Yeah, that means in medicine, an everyday application is imaging, medical imaging, and imaging means there is a noisy measurement of an original object, an organ, for example. And then the question was, is it possible from these noisy measurement to reconstruct the original object? To which degree of accuracy is that possible? And now that's a typical minimization problem, mathematically speaking, because noise should be reduced, minimizing problem. To which degree of accuracy is that possible? And that is a typical topic for machine learning, because neural networks could be trained by better and better samples to approximate the original object more and more. That means to approach the reconstruction of this original object. And that is a little bit a tricky proof, but actually then it can be shown, it can be mathematically proved that that is in principle by the digital computer only possible for some degrees of approximation. Now, the physicians ask me, has that practical consequences for us? Because we have not the ambitious idea to have rigorous approximation in the sense of a mathematician, but we are satisfied if it to some degree. Now, the argument is the targets of medicine are to becoming more and more reliable. And though the requests for accuracy are increasing. And so it is, of course, for the practical use, an important application that is only possible to some degree. Because in a mathematical sense, you can prove some lower bound of approximation. And then on the other side, the proof it could be possible, in principle at least, by this kind of analog computer, by neuromorphic computing, which I highlighted is. So in mathematics, you always get the framework of what is possible and what is not possible, principally, a priori. And I think that is an important message for the practitioners. That and now it depends, of course, on the practical application. Now, this is the link. That was my point here. The link between all these theoretical insights, even with practical application. And then, of course, you all know these consequences of more modern computer science, machine learning, for practical issues in surgery and so on, training robots and things like that. So the application to medicine will be amazing. In Munich, I'm also engaged. We are preparing a conference in the beginning of the coming year on supercomputers, and also in medicine, for example, or in astronomy and so on. These results of computing are enabling the new breakthroughs. It all depends more or less on the computational power here.
That's why the human and AI collaboration is important.
Mm-hmm.
So based on this, what fundamental changes are most urgently needed in our education systems to equip the next generation with the AI iteration and system thinking?
Yeah, that was my last point in my talk. Actually, education systems, and now to become elder and elder, I'm also feel responsible for that, the education, and how should we do that?
Yeah.
And my experience is some years ago I had a talk in Oxford. And then after that, we had also this this educational question. And the people told me there in the UK that their experience is that computer scientist education had a great failure missing, because that also my colleagues in the Technical University said me that 10 years ago. They said computer scientists, especially in Europe, in UK and Germany, for example, they are trained for programming.
Yeah, code.
So what is missed is a typical feature of a physicist. A physicist, that is amazing, is trained to have a model of the world, maybe in physics, maybe in economics, elsewhere. And then they are trained to have mathematical sophisticated tools to model it in a mathematical formalism. And then the mathematical formalism, that can be programmed. That is a computer science. So what is missed in computer science is the ability of modeling. And that is a crucial point. We need in the future the breakthroughs were by people who were able both. And sometimes the physicists are mathematically well trained, they are clever, and they made their computer scientists training by themselves, mainly. But what I want to say is they have not the ability to have an intuition, a model, and to describe that mathematically, this correlation. So physics is nevertheless a basic. You must not become a physicist in the end, but the education of this kind of considering the world, starting in modern times, that was Newton and Galilei, that was the beginning of modern science. Later on, chemists learned from the physicists to model the world. That was Lavoisier in the 18th century. And then in the next step, the biologists also came up with this idea to model the world. I mentioned the reaction diffusion equation, to model even organic systems in that way nowadays, even in medicine. This kind of thinking, that is crucial for the breakthroughs. So for the training, that means we need educational programs to connect and to integrate the education. That means computer science who are also trained in modeling, and the physicists who are also trained in computational issues. You could observe that in the second talk. these people here in this community, traditionally, they are electrical engineers. They were responsible for the electrification of the society in the past. But nowadays, they find the interface with computer science and in the second step with AI. So both modern electrical engineer is also trained in computability and vice versa. So I am highlighting that is a tendency in my whole academic career. I was also requesting the integration of these different approaches, these interdisciplinary approaches, because my observation in the history of science and technology is the great breakthroughs were always on the borderline of these disciplines. So this kind of interdisciplinarity, that is my plea for the future.
Yeah. As you are visiting China here, and what are you most looking forward to discuss with the scholars and the students here, and what is the most important advice for the young researcher and the students?
Yeah, for the young researcher and the students is exactly my last point, to be open-minded. Of course, you must be specialist. You must start in a special field, and then you must do your duty, and it depends on your abilities. If you feel attracted by medicine, do medicine. If you feel attracted by physics, do physics. Electrical engineering, do that. But then in your career, at least in the stage of your PhD, become open-minded, because the new breakthroughs are not on that strict line. Do not expect that your master thesis will be the breakthrough to all your problems for your future career. The world is changing. Be open-minded. You need some tools, but then that was my own experience. I started in logics and mathematics. But then, of course, I saw all these developments which were opened up, new avenues during my own development, and I had no ideas about that when I started. But I was also in my life very eager, and then I saw interesting connections to these fields, and then I did it. And I think that is my own experience, but I think it is also from a general point of view, it is necessary for the great breakthroughs. To find bridges, for example, a lot of my friends now, elder colleagues, are coming from medicine. And I learned a lot of medicine. I have no idea. I'm always with great respect to the complexity of the human organism, because with my physical and mathematical training, I have these nice ideas of a complex system. That if you are a physician, simple physician, then it is amazing to observe the reaction of the human organism. It is so complex, unbelievable. That means every day you are surprised by effects you never would expect by your theoretical insight. So I'm very eager now to to medicine, because it's so amazing to study this kind of complexity.
Yeah. So finally, my last question. Looking forward to the future of humanity in the age of AI. So what is the single most important question you believe we should be asking ourselves?
Yeah. I explained all these possibilities of humans in the future. Nobody knows exactly. The future is open. the future should be open.
Yeah.
That is also a request, because that was the experiment. If we try to stop anyway by rigorous limits the creativity, people, our species is so eager. That's typical for this kind of creativity for humans. You cannot stop. You remember the situation of Galilee by the church and others, state and so on. We had all these things. They try to stop and to help. You cannot stop human creativity. That's typical for our species, and that is the success of our species, that we are so eager. That is the one aspect. But on the other aspect, it is the insight that we, the humans, are in some sense distinguished here on our earth. That is this ability which we can observe in the history of technology and science. And that means that our species has a responsibility. We are the own species on this earth which in the end can help to save our planet and to influence our planet in its further development. We also have the ability to destroy. And that means the atom bomb, things like that. And so in the end, we have a lot of abilities, human creativity, but that is the ethical side, so to say. We also have the responsibility for the climate development, for the energy problem of our planet. And responsibility is my second important plea. And that means we must be aware of our power, but also we must be aware of our limits with respect to the whole Earth and species. And we have to consider both.